Welcome to the Deep Dive. Today, we're tackling some absolutely huge questions.
Really the biggest ones, aren't they? What is time? How did everything begin?
And crucially for our theme today, can we actually predict the future? We'll be looking at this through the work of Stephen Hawking.
Specifically, his book, The Universe in a Nutshell. It's quite something. He actually wrote it to be more accessible than A Brief History of Time.
More accessible? How so?
Well, he structured it like a tree, almost. You could jump around, skip the really dense maths if you wanted, and get straight to what he called the more exciting material.
Okay, so we're taking that cue. Our mission is to pull out the absolute core ideas, the nuggets that really shift how you think about reality, about cause and effect.
And definitely about prediction. What are the limits? That's key.
Absolutely. It's interesting how modern physics often highlights not what we can know, but the fundamental boundaries of our knowledge. And the starting point has to be Einstein, right?
Oh, definitely. His work in the early 20th century laid the groundwork for, well, pretty much everything that followed in cosmology and particle physics, two main pillars.
General relativity for the big stuff.
Stars, galaxies, the universe's structure.
And quantum theory for the incredibly small.
Atoms, particles, the fuzziness of reality itself. But before Einstein, the picture was, let's say, simpler, or at least seemed more intuitive.
Right, they had this idea of the ether.
Exactly, this invisible substance filling all of space. The thinking was, if light is a wave, it needs something to wave in, like sound waves need air.
Seems logical enough. Made for a nice, fixed background for the universe. An absolute space.
An absolute frame of reference.
Yeah.
But then came the Michelson-Morley experiment back in 1887, a real spanner in the works.
They were trying to measure Earth's motion through this ether, weren't they? By looking for tiny changes in the speed of light.
That was the idea. They expected light to travel slightly faster or slower, depending on whether it was moving with or against the ether wind.
And they found
Nothing. Absolutely nothing. The speed of light was stubbornly, frustratingly constant, no matter how the Earth moved, no matter how the observer moved.
which just completely shattered the ether concept.
It did. And it paved the way for Einstein's special relativity. If the speed of light is the one constant thing for everyone,
Then something else has to give. And that something was time.
universal time had to go. Instead, Einstein introduced the idea of personal time. Your time depends on how you're moving.
It sounds so theoretical, like something out of science fiction. But it's real, isn't it?
Measurable?
Oh, absolutely measurable. They proved it. You know the experiment with the atomic clocks?
Vaguely, yeah. Flew them around the world.
That's the one. Highly precise atomic clocks. One flew eastward, with the Earth's rotation effectively moving a bit faster. Another flew westward, against rotation.
And the eastward clock.
Recorded slightly less time had passed. Tiny amounts, fractions of milliseconds, but enough to prove it. Your personal time literally ticks at a different rate depending on your velocity. And, as we'll see, gravity too. So the idea of a single now across the whole universe.
It's an illusion. Simultaneity is relative. That's special relativity.
Okay, so special relativity deals with constant speeds.
Yeah.
But what about acceleration? And what about gravity? Newton's gravity was instantaneous, right? That clashes with the light speed limit.
Big clash.
No.
A huge problem for Einstein. He needed a new theory of gravity, and that led to general relativity. And this is where things get, well, even stranger.
How so?
He connected gravity to the geometry of space-time itself through something called the equivalence principle.
The equivalence principle. Okay, break that down for us.
Imagine you're in a sealed box, no windows, like an elevator in deep space.
Okay, I'm in the box.
Now, if you feel a force pulling you down to the floor, can you tell if the box is sitting still on Earth feeling gravity, or if the box is accelerating upwards through space at 9.8 meters per second squared?
Sealed box. I guess not. The sensation would feel identical.
Exactly identical. And that, Einstein realized, was the key. If gravity and acceleration are indistinguishable, then gravity can't be a force pulling things across space in the Newtonian sense.
So what is it then?
It's the shape of space and time. Mass and energy literally warp space-time. They create curves, distortions.
Like the bowling ball and the rubber sheet analogy.
Precisely. The bowling ball, like the sun, creates a dip. A marble rolling nearby, like Earth, isn't being pulled by the ball, it's just following the straightest possible path on that curved surface.
So planets orbit because they're following the curves in space-time created by the sun's mass. not because of some invisible tether.
That's the essence of general relativity. Gravity is the curvature of space-time.
Wow. Okay, that changes everything. Space and time aren't just a static background anymore.
They're active participants, they affect matter, and matter affects them. They're dynamic. And this dynamic nature immediately points to a massive question.
The beginning.
The very beginning, the Big Bang. See, if time itself is part of this dynamic fabric defined by things within the universe.
Then time itself must have a beginning if the universe did.
Right. Which makes asking what happened before the Big Bang kind of meaningless. There was no before if time itself started then.
General relativity actually predicts this beginning point, doesn't it? The singularity.
It does, a point of infinite density, infinite temperature, infinite space-time curvature, where all the known laws of physics just stop working.
And Hawking, along with Roger Penrose, actually proved theorems about this.
They did, back in the late 60s, showed that under general relativity, a singularity was inevitable in our past. They even won a prize for it.
How much?
Believe it or not, $300 from the Gravity Research Foundation for figuring out the origin point of the universe, essentially.
$300. Bargain. But that singularity, that infinite point, it's a problem, right? A wall for classical physics.
A huge wall, and that's where the other great revolution comes in, quantum mechanics.
The physics of the very small. The realm Einstein famously distrusted. God does not play dice, he said.
And yet, it seems he does. Quantum mechanics is fundamentally probabilistic. At that level, things don't have definite properties until you measure them.
You mean like a particle doesn't have a precise position and speed?
Exactly. It's described by a wave function, which just gives you the probabilities of finding it here or there with this speed or that speed. It's inherently uncertain.
Like rolling dice. You can't know the outcome of one roll for sure.
But you can predict the average over many rolls. That's why the macroscopic world seems predictable. It's the average outcome of countless quantum events.
But the early universe wasn't macroscopic. It was tiny, incredibly dense.
The size of a grapefruit, or even smaller initially, absolutely dominated by quantum effects. Quantum randomness was king.
So if the universe was governed by quantum rules at the start, it couldn't have had just one single predetermined history.
That's the crucial insight. Which leads us to Richard Feynman's idea, a really radical one.
The sum over histories.
That's it. Feynman proposed that to get from the beginning to where we are now, the universe didn't just take one path. It took every single possible path simultaneously.
Every possible history. How does that even work?
Each possible history has a certain probability or amplitude, and the actual universe we experience is, in a sense, the sum, the interference pattern of all those possibilities.
Okay, my head hurts already. If there are infinite possible histories, how do you calculate anything? How do you even define the starting conditions, the boundary of the universe?
That's the exact problem Hawking tackled with James Hartle. Their solution is often called the no-boundary proposal. It's the core of the nutshell idea.
No boundary. How do you have a universe with no beginning boundary?
This is where it gets really clever and maybe a bit weird. They introduce the concept of imaginary time.
Imaginary time. Okay, that sounds made up. Is it just a mathematical trick?
It is a mathematical tool, but a profoundly useful one. Think about regular time, the time we experience. It flows forward one direction. It's distinct from the three spatial dimensions.
Right. Length, width, height, and time.
But in their model, using imaginary time, which mathematically behaves like multiplying time by the square root of -1 time, essentially becomes like another dimension of space.
So, 4 spatial dimensions, in a way, using imaginary time.
Sort of. The key thing is what it does to the beginning. In real time, the universe's history looks like a cone starting from a sharp point, the singularity, a point where physics breaks down.
The wall we talked about.
Exactly. But if you trace the history in imaginary time, you can smooth out that point. The history of the universe becomes a closed surface, finite in extent, but without any boundary, edge, or singularity.
Like the surface of a sphere.
Precisely. A four-dimensional sphere-like surface. It has no beginning or end point. It just is. Self-contained. That's the nutshell. A universe without a boundary in imaginary time.
So, by using imaginary time, you eliminate the need for a singularity, and you eliminate the need to ask what came before or what set the initial conditions.
That's the beauty of it. The boundary condition is that there is no boundary. The universe is described entirely by the laws of physics within it. No external creator or special starting point needed.
That's a profound philosophical shift. But if there are countless possible histories allowed by quantum mechanics, maybe even by things like M theory, why this universe? Why the one we see?
Good question. If there's a whole landscape of possible universes or histories, what picks ours out?
This sounds like where the anthropic principle comes in.
It does seem to play a role, yes. The idea is, well, the universe has to have properties that allow life like us to develop within it, otherwise we wouldn't be here to observe it.
So we filter the possibilities just by existing.
In a way, it sounds a bit circular, maybe, but it has real constraints. For example, Hawking points out we need 3 large, flat spatial dimensions.
Why 3? What if there were 4?
Uh,
Or 2?
If there were 4 or more large spatial dimensions, gravity and electromagnetism would fall off too quickly with distance. Stable orbits for planets wouldn't be possible. Atoms might not even be stable.
And with only 2?
With only 2 dimensions, life gets tricky. As Hawking puts it, if you had a gut running through a 2-dimensional animal, it would split the poor creature in half. Complex structures seem to need 3 dimensions.
Okay, that's graphic. But isn't the anthropic principle sometimes criticized? Like, it explains things by saying it has to be this way because we're here.
That is the main critique, that it might lack predictive power. It's just post hoc rationalization, but it does frame the problem. And crucially, it connects to actual observations.
Like the Kobe satellite data, the map of the early universe.
Exactly. The no-boundary proposal in imaginary time suggests the most probable history is one that's very smooth, almost perfectly uniform.
But a perfectly smooth universe wouldn't form stars and galaxies. It'd just stay smooth.
Right. We need some initial bumps, some fluctuations, and that's precisely what Kobe found. Tiny temperature variations in the cosmic microwave background radiation, the afterglow of the Big Bang.
Ripples in space-time.
Ripples of about 1 part in 100,000. Just enough deviation from perfect smoothness. These tiny quantum fluctuations stretched across the expanding universe were the seeds of galaxies, stars, and ultimately us.
So the observations support a history that is mostly smooth, like the nutshell idea predicts, but with just the right kind of small wrinkles or hair needed for structure.
Exactly. The slightly hairy nutshell seems to be the most probable history that also allows for our existence. The anthropic principle filters the possibilities, and Kobe confirms the necessary wrinkles were there.
Okay, we've gone from the beginning of time through quantum histories. Now let's talk about messing with time. Time travel. General relativity seems to allow it, doesn't it? If space-time gets warped enough.
Theoretically, yes. The equations permit solutions that contain what are called closed time-like curves, or CTCs.
Paths through space-time that loop back on themselves.
Essentially, yes. You could, in principle, travel along such a curve and arrive back at your starting point in space before you left in time. Think wormholes, or perhaps near rapidly rotating cosmic strings.
Which immediately brings up the grandfather paradox.
The classic problem. If you can go back in time, could you prevent your own grandfather from meeting your grandmother, thereby preventing your own birth? It's a logical nightmare.
A paradox that suggests maybe such travel is impossible? Hawking certainly thought so.
He proposed the chronology protection conjecture. Basically, he bet that the laws of physics themselves would conspire to prevent macroscopic time travel into the past.
How? What's the mechanism?
Well, classically, to create and stabilize something like a traversable wormhole, a shortcut through space-time that could act as a time machine, you'd need exotic matter. Matter with negative energy density.
Stuff that weighs less than nothing.
Effectively, yes. And classical physics generally forbids that on large scales. Things have positive energy.
But quantum mechanics is weird. Does it allow negative energy?
It does, sort of, on very small scales, through virtual particles. Empty space isn't truly empty. It's fizzing with pairs of particles and antiparticles popping into and out of existence. One particle in the pair can have negative energy balanced by the other's positive energy for a fleeting moment.
Okay, so quantum mechanics provides the negative energy loophole. Time travel back on the table.
Not so fast. This is where Hawking argued the quantum effects actually prevent time travel. Imagine you're trying to create the conditions for a time loop, maybe at the mouth of a wormhole. You're creating a boundary, a horizon, beyond which the time loop exists.
Right.
Those virtual particles near this horizon can get caught. One particle might fall into the time loop region while its partner escapes. Worse, particles can get trapped on the boundary, circulating around the loop.
What happens to them?
As they circulate near the speed of light on this forming time loop boundary, they get incredibly energized. It's called blue shifting. Their wavelengths get shorter and shorter, their energy higher and higher.
Towards infinity.
Towards infinite energy density right on the horizon itself. It's a runaway feedback loop. The very attempt to create the time machine generates this catastrophic energy surge.
Like a bolt of lightning guarding the entrance to the past.
That's a perfect analogy, an infinitely powerful burst of radiation that would destroy the wormhole, or certainly prevent any macroscopic objects like you or your spaceship from actually crossing into the time-traveling region. Quantum effects slam the door shut.
So causality is safe.
According to the conjecture, yes. The probability of macroscopic time travel actually occurring is estimated to be vanishingly small. Hawking calculated it as less than 1 chance in 10, followed by, well, a number with about 60 zeros.
A trillion, 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 trillion zeros. Okay, so practically impossible.
For all intents and purposes, physically impossible. The laws of physics protect the timeline.
Which brings us back to our main theme, the limits of prediction. We started with classical physics, Laplace's demon. The idea that if you knew everything now, you could predict everything forever.
Total certainty. But quantum mechanics threw a huge wrench in that with the uncertainty principle. Suddenly, you couldn't know position and momentum precisely. Prediction became probabilistic. Our predictive power was essentially halved right there.
And now you're saying there might be an even deeper limit, related black holes.
Potentially. There's a huge unresolved issue in physics called the black hole information paradox. When a black hole evaporates via Hawking radiation, does the information about what fell into it get destroyed forever?
If information is lost.
Then our ability to predict the future, even probabilistically, could be fundamentally compromised. Because prediction relies on information from the past state. If that information can be utterly erased, then prediction might, in some deep sense, be reduced to zero. The universe might be fundamentally unknowable in its totality.
Wow. From personal time to curved space-time, quantum foam, multiple histories, and finally, physics protecting causality itself while possibly erasing information. It's quite a journey.
It really is. And it leaves us with a fascinating final thought, stemming from that positivist view. Hawking often took the idea that a scientific theory is just a mathematical model that describes observations.
Reality is the model.
Or at least the model is the closest we get to reality. So if we find ourselves needing concepts like imaginary time, a purely mathematical construct, to make sense of the universe's origin, to build a consistent boundary-free model.
Yeah, what does that say about the line between real and imaginary in our understanding of the cosmos?
Exactly. If time and space are defined only by measurements within the universe, and our best description relies on a mathematical tool like imaginary time, how solid is the distinction between the mathematical description and the physical reality it represents? Something for you, the listener, to ponder. What is truly real?